Hello everyone. So this is the introduction of function. So before we define or give an example of what function is, let's try to take a moment to consider its background. All right. So let's just say we have two sets. We have this one, the first set. Let this first set be represented as. So in this set, I have four numbers. All right. So these are 8, 9, 25, and 35. All right. Then I have the second set, which I will be representing it as letter Y. So I'm going to have three numbers only. So this would be 2, 3, and 5. All right. So I have like a statement here. Okay. Blank is divisible by blank. All right. So the next thing that I'm going to do here is that I'm going to match the numbers from this set, which is set X, to set Y, based from the given statement here. Basically, the numbers from X here is divisible by the numbers from the set Y here. So we're going to match the numbers given here, all right, from this set to the numbers here in set Y based on the condition here. So first, let's start with 8. 8 is divisible by what number here? So 8 is divisible by 2. All right. Next, 9. 9 is divisible by what number? 3. Next, 25. 25 is divisible by what number? 5. Well, how about for 35? Well, we all know that 35 is divisible by 5 itself. So we can match 35 to 5 here as well. Excuse me. So seems like we already match the numbers from set X to set Y based on this condition. So what we're going to do is we're going to pair them up. All right. So by pairing, since in set X, they are the ones are responsible in matching themselves to the other number on different set. So this is the format of what we're going to do. So parenthesis X, comma, Y. All right. So you see this X right here are this one. All right. And this set is responsible for matching. All right. On the other hand, for Y, these are the matched elements by the elements from that X. Basically, they are being matched by the numbers here. All right. So we're going to pair them up in this format. So let's start first with 8 and 2. Since we have 8 and 2 here, we can just write it this way. 8, comma, 2. That means in here, 8 is your what? The number here from set X, the one who is matching. This number 2 is the one that is matched by the number 8. All right? So let's try this one. 9, 3. So we have 9, comma 8. So since that we have this one, 25 to 5 and 35 to 5, how can we do that? We can just simply separate it. So we can just do it this way. 25, comma 5, and 35, comma 5. So you see, the numbers from set X, as I told you, they're the ones who is matching. While the numbers in set Y, they're the ones who are matched by the numbers given in set X. All right? So this number from set X is 8, 9, 25, and 35. Here in this set, since they are the one who is matching, these are what you call as the input. All right? This set is called as the input. So the numbers here in this set, you can rename it as inputs or input numbers. While to those numbers that are matched by these numbers, so we have like 2, 3, and 5. So since they are matched by these numbers in set X, we can just represent this one as output. So for each element or numbers given in this set, which is in particular set Y, you can just describe them as the outputs or output numbers. All right. So as you can see, the input numbers are actually on the left, on the left side. All right. Then the outputs, they are on the right side. All right. So now that I already mentioned these pairs, this one, you know, I'm sorry, these, since there are four of them, these pairs, we can call them as ordered pairs. Hold on, sir. All right. So if you ever see this format, like for example, 8 comma 2, and then there's like a parenthesis, you know, parenthesis outside them. So that format is called called an ordered pair. All right, just like this one. All right, two elements. All right, and between them there's a comma, and outside them there is a parenthesis. All right, so let me rewrite these ordered pairs into a set. So this is 8 comma 2, 9 comma 3, 25. Oh, sorry. Let me fix that 5 here because that doesn't look 5 from me. It looks like 6. 25 comma 5 and 35 comma 5. So it seems like I made them into a collection of ordered pairs. So basically, since I again what do you call this one illustrated these sets and then I paired them up into a format so-called ordered pairs, now I made them as a collection of all of the ordered pairs given or presented from this diagram of set. So now that I made a what do you call this one a collection of these ordered pairs, Now, what do I call this one? A collection of ordered pairs, you know. So this collection of ordered pairs is what you call as relation. All right. So again, if we collected all of the ordered pairs, or yeah, basically the given ordered pairs, like all of it in a certain what do you call this one, sets or diagram or equation, and then we have these ordered pairs collected, all right, based from this example is what you call as the relation. So let's proceed to the next slide to sum up what is the relation. So basically, relation is a collection of ordered pairs, just like this one. All right. Since I already mentioned all of the given ordered pairs here, so these are the what? Ordered pairs. All right. So there are two components. We have the domain and we have the range. So before that, let me copy the ordered pairs earlier. So first, we have 16, comma 2, 9, comma 3. Then we have 25, 5, and we have 35 and 5. There we go. So in this collection, let's determine domain and range. So before that, let's identify what is domain and range. So for domain, it is a collection of independent variables, or you can just say inputs or input numbers, or you can call them as abscissa. All right. So you see, domain is sorry, the independent variables are always located here on the left part, always. All right. So again, where does the independent variable or inputs or abscissas are located? So they're located on the left part of the ordered pairs. Oh, yeah, left part of a ordered pair. So that means the domain, right, of this relation is 16. Oops, sorry. Ah, yeah. Yeah, we can just write that first. Yeah, 16, 9, 25, 35. Oops, I think let me fix the bracket. Um, it's triggering me. There we go. Now this I try. 16, 9, 25, and 30. Then next, how about for the range? So range is a collection of dependent variables. All right, dependent variables. Or you can describe them as outputs or ordinates. All right. So where would you locate the dependent variable? So since the independent variable or input is located on the left part of a ordered pair, the dependent variable or output number, on the other hand, is located at the right side of an ordered pair. Right side. All right. Therefore, the range of this relation is what? The range of this relation is 2, comma, 3, comma, 5. So 2, 3, and 5 are the numbers in range coordinates or component. All right. And plus it makes sense because if you would go back to the previous slide, I told you that is example. We have in this set, as you can see, these numbers are the ones who are matching. And are matching are what you call as the inputs or input numbers. And hence, this set X is represented as the input. While in this set, as you can see, they are the ones who are matched by the element in set X here. So since they are matched by the numbers from set X, then this set Y is represented as the output. All right. So as you can see, the output numbers are located on the right side, while on the input numbers is located on the left side. All right. So that's it. So again, before we proceed, relation is a collection of ordered pairs. All right. So if you have a given ordered pairs, and if I ask you, what do you call this group of ordered pairs given from this a example? This is what you call as the relation. Group of ordered pairs. All right. So that's it. So how can you illustrate relation? So there are four illustrations. First is by mapping diagram. Second is by table. Third is by ordered pairs. And fourth is by equations, which is to be discussed soon. All right. So let's start first with mapping diagram. So in mapping diagram, this one is just the same as what we did in the first slide, which is, having two sets. All right. So there are three types. All right. The first type is what we call as the one-to-one mapping diagram. So what does one-to-one mapping diagram look like? So let's just say I have two sets. All right, let's just say I have two sets. So let's just say this is 1, 2, and 3, and then this is 2, 4, 6. All right. So I'm going to match them randomly. All right. And then you will notice the difference. So let's just say 1 is to 2, then 3, 4, 2. So what did you notice in this diagram? So as you can see in this diagram, the element from, wait, let me represent this as X and Y. There you go. That would be far more convenient. So the element from the set X have a, let's just say, a association or relation, or to put it simply, match to one of the elements in set Y. So 1 to 2, then 2 to 6, 3 to 4. That means each of the elements in set X has its own matched element in set Y. Only one. Right? Only one. All right. So let me give you another example. So let's just say I have another set. So let me just represent this as X. All right. So let's just say this is 3, 6, 9. All right. And then we have another set Y here. And I'm going to represent this one as 4, 8, and 12. So I'm going to match them out randomly. So this would be 3 to 4, 6 to 8, 9 to 12. What did you notice here? So the same implication as the first example here above, basically each of the elements in set X has its own element in set Y. Only one. So 1 to 1, 1 to 1, 1 to 1. Same thing here. 1 to 1, 1 to 1, and 1 to 1. That's it. All right. So that's for the 1-to-1 diagram. Hold on, hold on. Let me rewrite it again. So how about for the second diagram? The second diagram, this is what we call as the 1 to many diagram. So when it comes to 1 to many diagram, it looks like this one. So same example as 1, 2, 3. So let's just say I have 1, 2, and 3. Then for the set Y, same thing. Let's just say I have 2, 4, and there we go. So let's match them. All right. So let's just say I match what do you call this one? Let's just say I match 1, 2 here, and then this one 2, I match it to 4 and 6, and then let's just say wait a minute, I think I missed. Hold on, hold on. I forgot one number here. Sorry, sorry guys, I forgot one here. Let me add another one. All right. Let me add another one here, guys. Okay, going back. So 2, 4, 6, 8. All right. So let 3 match to 8. Right, there we go. Sorry guys, I forgot to put 8 here. All right. So let's go back. So what did you notice from the first diagram and to this second diagram? So as you can see in the first diagram, as you can see, in one element connects to one element only. You know, from 1, 1, 1, only one, and one from here and one partner only. All right. On this case, as you can see, 1 is matched to 2. All right. 3 is matched to 8. However, in this part, we see 2 is matched to 2 elements in set Y. So 2 to 4, 2 to 6. So you see, this is one of the example of one-to-many diagram, in which, as you can see, 2 is matched to more than one element in other set, which is like this one. 2 has, wait, I'm sorry, number 2 has 2 matches, 2 to 4 and 2 to 6. So this is no longer one-to-one, but it is called as one-to-many diagram. All right. So this one is no longer one-to-one. Unlike here, each of the element has only one partner. So 1, 1, 1, 1, and so on and so forth. This one, either one of them, right, one of them here, or maybe two possible, has two elements matched to that Y here. All right. So that's for the second diagram. So let's now proceed to the last type, which is the reverse version of this one. So this is many to one diagram. So as always, there will be two sets. Let's just say from this set, I have 1, 2, 3, and 4. And from this set, I have 2, 4, 6. All right. And let's just match them. So let's just say 1 is for 2, 2 is to 4. Then we have, hold on, 3 is to 6, and 4 to 6 as well. So what can you see here? So as you can see in this diagram, if you're going to compare it to the second diagram, which is one to many diagram, so it seems like it's the reverse. From one to many diagram, as you can see in this one, all right, there's only one element here given, and then on the different set, which is set Y, there are more than one element matched by this element from set X. On the other hand, all right, so there are two elements, all right, two elements from set X connected or matched to one of the elements in set Y. So meaning this one is many because it involves more than one element to match to only one element here in set Y. So from here we have one, two, many elements. From here we have many elements since it consists of more than one element connected to this. Hold on, sorry. There you go. Connected to this one element only, which is so. Hold on, let me erase this. At least now you guys have the idea what does these mapping diagrams look like. All right. Okay. So to sum it up, from the first diagram of mapping diagram, I'm sorry, first mapping diagram, we have one-to-one. So meaning in here, in one element from the set X, okay, is matched to only one element from set Y. So basically one-to-one. One partner, one partner. One partner, one partner, and so on and so forth. For this one, on the second type of diagram, which is one to many, meaning either one or more than one element here has two two matched elements from set Y, such as this one. As you can see, from here we have number 2. We have only one element here from set X, yet it is connected or matched to two elements from set Y, which is 4 and 6. And lastly, we have many-to-one diagram, which is the reverse version of one-to-many diagram, wherein in this set X, there are more than one element matched to one element here in this set Y. So just like this one, we have two elements such as 3 and 4, all right, connected to only one element here, all right? So this is what we call as the many-to-one diagram, all right? Next is we have table. This one is simple actually. This one is simple, all right? Table, it could be in a vertically oriented way or horizontally oriented. So let me give you a simple example. So let's start with the horizontal one. So let's just say, all right, we have this one, X, and then we have Y. So let's just say I have, wait, let me draw a borderline, all right? Forgive me if it's uneven. As you can see, the alignment of the line and its drawing is not good. So please just visualize it. All right, just visualize that it is a perfect set of tables. All right. So let's just see what we have here. So here, let's just say in for x, so x is the input. All right. So let's just say I have 1, 2, 3, 4, and then we can have here as for y as the output. Let's just say we have this one, 3, 6, 9, 12. See? Or we can do it vertically oriented way. So we have x, y. That's it. Here, we'll on 1, 2, 3, and 4. That's it. There we go. All right. So I just copy the given here. So in x, we have 1, 2, 3, 4. So in here, in for y, we could have 3, 6, 9, 12. All right. So that's it. All right. So this one is basically horizontal oriented table, and this one is vertically oriented table. All right. So why is this like important? Like yes, we have mapping diagram, yet we also have table as well. This one is important also in determining your ordered pairs, which is to be discussed later on. All right. So there could be another type of table actually. All right, we're in. All right, let's just say we are going to make it in a horizontal oriented way. So the same thing, we have x, and then we have y. All right. Let's just say I have, all right, 1, and then I have, oops, sorry, I think I use different. I mean, I should be using different colors. 1, 2, 3, 4, 5, and 6. Let's just say I have 1, 2, 3, 4, 5, and 5. Let's just say. Then here for y, let's just say I have 2, 4, 6, 8, 10, 12. So as you can see, it seems like we have the same number, 5 and 5, right? From the input row, which is from your x. Yet, yet, there is two different numbers. What does this mean? All right, it means if you're going to put it on ordered pair, what does it look like? So from here, 1 and 2, so you're just going to write this as 1, comma 2. Simple. This one, 2, comma 4. This one, 3, comma 6. This one, 4, comma 8. But how about for this one? So for this one, we can just simply write it as 5, comma 10, then 5, comma 12. See? Meaning, okay, 5 has two two outputs, and that is 10 and 12. All right. There you go. So that you won't be confused. So again, if we encounter this one, the same what do you call this one? The same input numbers as 5 and 5, and then each output is different. What do you call this one? Different numbers. Then that means 5 has two outputs. Okay, which is 2 and 12. 2 and 12. Sorry, 10 and 12. And if you're going to rewrite it in ordered pair, you can rewrite it as this one, 5 comma 10 and 5 comma 12. All right. And you can also rewrite it in vertically oriented table, such as this one. All right. And speaking of vertically oriented table, let's try to have one more example. Hold on. Let me erase this one. Okay. So let's just say I have a vertically oriented table. So this is X, and then we have Y here. All right. So this is 1, 2, 3, 4. And I think we can stop here. Would be the fifth row. I mean, sixth row if you're going to include X and Y. So let's just say we have negative 1, 0, 1, 2, 3. And then you have the outputs. All right. So for the outputs, you have 1, 0, 1, 4, 9. So what did you notice? If you notice that here we have negative 1, its output is 1, right? And we have 1 here, which is on this one located here. And then its output is the same as the output for the negative 1, which is 1. So as you can see, what if they have different inputs but the same output? Different input but the same output. If earlier, the same input but different outputs, right? Remember the 5 is connected to two numbers, which is 10 and 12. Well, how about this one? This one is completely reversed. So we have two numbers, which is negative 1 and 1, have the same output, which is 1. So what does this mean? All right. So if you're going to rewrite it in ordered pair, how is it going to look like? So this would be negative 1, comma 1. Then we have 0, comma 0. Then we have 1, comma 1. Then we have 2, comma 4. Then we have 3, comma 9. All right. So as you can see, we can still rewrite it this way. So the same pattern as usual. All right. What would be the input and output? Just pair them up. Finish. That's it. But if you want me to put it on mapping diagram, this is how it looks like. We have like negative 1, 0, 1, 2, and 3, right? And we have what? The numbers here are basically 1, 0, 1, 4, 9. Oops, hold on. There shall be no repeating numbers here. This would be again 1, 0, 4, 9. So as you can see, we have negative 1 and 1. Their output is the same, which is 1. So negative 1 to 1 and 1 to 1. So what do you call this one? If you have more than one element from set X connected to only one element in set Y. This is what you call as the many-to-one diagram already. All right. So to be specific, let's just remove the other numbers except negative 1 and 1. All right. This is how it looks like. All right. So earlier, if you remember the numbers, 5 is connected to 10 and 12. All right. If you notice that one input connected to more than one element in output set or set out outputs, then that is what you call as the one-to-many diagram. However, in this case, this is already different. Like from the set of inputs, okay? So we have more than one element from set X matched to what sorry, matched to only one element in set Y, which is this one. So from many, since we have more than one element connect to only one one element from set Y. All right. See, that's it. So this is one of the reasons why relations could be illustrated by table. Okay, it could be represented as this way. All right. So okay. Now this one, I think I already simply discussed it already to you. You know, ordered pair. All right. So ordered pair is just basically the format of it is just like x comma y. So remember that this one is your input as always. This one is your output as always. All right. So what would have happened? All right, if we're going to have an example of ordered pairs, so we can have an example. Like for example, I have the first set of ordered pairs. So I have 1, comma 3, 2, comma 6, 3, comma 9. Then we have 4, comma 12, and yada yada yada. I can also have another ordered pair. All right, so let's just say 1 to 1, then 1 to 1 to 2, then let's just say 2 to 3, then we have 3 to 4, and yada yada yada. All right, and we can have another example. All right, this one's actually easy, but you have to take a look the numbers here and the way how they arrange. All right, if you think that there's some of them, some of the ordered pairs have similarities to other ordered pairs given in a set. So be very careful of that. So again, let's go back here. So let's just say I have this one. So 1, comma, let's just say 1, comma 0. Then let's just say 2, comma 0. Then let's just say we have 3, comma 1. Then 4, comma 2, and yada yada yada. So I want you to look at the first example. Okay, the first set of the ordered pairs, which is this one. All right. So 1, 3, 2, 6, 3, 9, and 4, 12. So what did you notice? So as you can see, this one, 1, 3, 2, 6, 3, 9, 4, 12, they have their own element actually. Okay. So the numbers, okay, the numbers or element from this to this to this to this may not be, you know, the same. All right. If you notice it, if you notice the pattern here, look at the dominant here. Again, how do you again find the dominant? I'm sorry, the domain of the relation here. The domain is here, right? 1, 2, 3, and 4, right? So basically 1, 2, 3, and 4. The range, how would you determine that? The range is on the top right. So this would be 3, 6, 9, 12, right? So what did you notice here? So you see from the domain of this relation, they don't have what do you call this one? The same number to each other. And same thing here as well from the range. Okay, each of the elements here, they do not have the same number. Like it's unique. Like from here, 1, 2, 3, 4, 3, 6, 9, 12. That's it. All right. So that's for the first example. But how about for this one? What did you notice? If I ask you to find the domain of this second example, what would that be? So obviously it's the left part, right? So this would be 1, 2, 3, right? But before that, let's go back again. We have 1, 1, 2, 3. Meaning, as you can see, in this ordered pair, we have what? We have the same input, yet different what? Different outputs. So meaning, if I'm going to put it at this way, I have 1, and then 1 has 2 outputs. So this is colon, colon. So this is 1 and 2. As you can see, 1 and 2. But they have what? The same input, which is 1. So 1 and 1 and 1 and 2. So just like this one as well. So let me continue in finding the range. So the range for this relation is 1, 2, 1, 2, 3, 4. All right. So for the relation, they are completely unique. Right? For the relation, they're completely unique. 1, 2, 3, and 4. So no the same numbers. Just the same as the first example. All right. Except that in domain, you have the same number here, which is 1 and 1. Yet each of them has its own outputs or output numbers. So it seems like one has two outputs, which is 1 and 2. So what do you call this mapping diagram? So this is what? 1 to many. All right, this is 1 to many diagram. Because as you can see, there are two ordered pairs that has exactly the same independent variable, which is your 1 and sorry, wrong, what do you call it? Wrong word. The same independent variable, which is 1, but different output number, which is 1 and 2. So from this first term, we have 1 and 1. So the 1 here is the output. Then from this one, on the second term, we have the input of 1, and then its output is 2. So that's completely different from the first ordered pair. So this one. All right. So this is 1 to many. So how about for the last one? So what did you notice here? Let's find the domain of this relation. All right, or basically short for collection of ordered pairs or set of ordered pairs. So for domain here, this is 1, 2, 3, and 4. So these numbers are completely unique. You know, they're completely unique. For range, what would that be? Let's find the range. So for range here, this would be 0, 0, 1, and 2. So this would be 0, 1, 2. So before we stop right here, um, let's observe this and this. What is the similarity and difference between these two ordered pairs? So as you can see, the inputs are completely different. They're completely unique. Like we have 1 and 0. Then for the next for the next ordered pair, 2 and 0. However, look at the output. It's 0 and 0. So meaning, in this ordered pair, the input is 1 and sorry, yet the output is 0. And the same thing here as well from the second ordered pair. The input is 2, but the output here is the same as the output here in the first term, which is 0. So what does this mean? It means that this is, wait, hold on, let me put it this way. 1, 2, right? And then we have, oh, wait, sorry. Let me rewrite it this way. So we have two elements from X match to only one element from set Y, which is 0. So as you can see, 1 and 2 have the same output, which is 0. So 1 comma 0 and 2 comma 0. So this means this is a many to 1. Alright, this is many to 1 diagram. Alright, excuse me. Do you see that? So this one is very important for you to determine because it is very useful if you would know if this ordered pair is relation, obviously, but there's something, a special kind of relation that you will know later on. All right. So remember this one, guys, because this one, especially the table, the mapping diagram, please remember this one. All right, because we're going to use it in the next slide. So at least you got the idea of it. All right. So for the equation, this one, I'm just going to discuss it on the future, all right, in future videos. All right. But I'm just going to write it this way. Okay. But again, I'm going to discuss it in the next videos, next time. So in equation, okay, we can determine relation by examples, all right? These are the examples. By, we have this equation, y is equals to 3x minus 1. We can determine the relation in this equation, x squared plus y squared is equal to 4. We can determine the equation in this formula, y is equal to x squared. Oops, sorry. Y is equals to x squared. And lastly, we can determine the equation. Equation is this relation, which is x squared minus y squared minus 1 is equal to 0. So these are the examples of equation that I'm going to discuss in the future. All right. But there are more equations that I'm going to include, all right, aside from these four equations. But yeah, in every equation, there is always a relation. So such as this one. All right. But there's one thing that we need to be aware of. All right. So as I told you earlier, there is like a special special kind of function relation. I already mentioned it. Damn it. I'm sorry. All right, there you go. There's a special kind of relation. All right, and what is this special kind of relation? All right. So first we have mapping diagram. All right. In mapping diagram, for this special kind of relation to exist, make sure that in the mapping diagram it could be either, all right, either one-to-one diagram or many to one diagram. All right. Number two. All right. For the special kind of relation exists, make sure that in the table, each independent variable or input has exactly, oops, hold on. Let me fix that handwriting. Has exactly one one output. All right, only one output. All right. For ordered pairs, oops, that's not a good handwriting. Let me fix that. All right, that's not a good handwriting. Hold on. There we go. For ordered pairs, all right, the same thing here, right? Same as in table, meaning each input has exactly one output. All right. And lastly, for the equation, which is to be discussed in the later videos or in future, for the equation, okay. So for this special kind of relation exists in equation, make sure that the again each what do you call this one? I think I do not need to write it. Each input has exactly one output. So meaning same as in table. All right, same as in table. So hold on. Let me put a parenthesis so that we will not be confused. So what does this mean? So first, in mapping diagram, make sure that it is one-to-one diagram or many-to-one diagram. For a table to exist, make sure that each input has exactly one output, has exactly one output only. For ordered pairs, the same as in table. Make sure each input has exactly one output. And the same thing as in equation. Make sure in equation, it produces, okay, different outputs in which each input has exactly one output. So, in general, what is this special kind of relation? All right, what is this basically? So this one is what we call as the functions. Okay, function is a kind of relation that exactly one element of range corresponds to the domain. Only one. All right, only one. So before I fully explain this one by one, except for this one, because this one is, for the next video, right? This one's for the next video. Yeah, next video. All right. So before I'm going to discuss mapping diagram, table, and ordered pairs in function way, all right, I'm going to, introduce you what is the notation of function looks like. So function, okay, for example, we have uh, y, right? So we can use f of x, okay? Or you can just use different letters, right? We have f of x. We can use g of x, we can use h of x and many more letters that we can use. All right, many more. All right. So as you can see, these, all right, are the notations. All right, notations of a function. So for example, I have y is equal to 3x minus 1. I can just simply rewrite this as f of x is equal to 3x minus 1. All right. Or I can rewrite this as g of x is equal to 3x minus 1. All right. So it's up to you. Right. Or it depends on the given set. So let's go back. All right. Because I know that most of you are confused at this one. Okay. How would I know that this is function? All right. So let's go back to the mapping diagram. So again, you will know if it is a function if it is one to one or many to one diagram. All right. So let me give you an example. So let's just say I have 2, 4, 6, 8, 10. And I have a second set. All right. Let's just say I have 0 0.5, 0. Wait, hold on. Wait. There we go. 0 0.5, 1, 1.5, 2, 2.5. So let's just say I have a given example. Let's just say I match 2 to 1, I match 4 to 0 0.5, I match 6 to 2, I match 8 to 2.5, and I match 10 to 1.5. So what type of mapping diagram is this? So this one, as you can see, each of the elements from the first element, let me just put this as x and y, right? X and y. So each of the elements in set X has only one element in set Y, all right? Or from set Y. And as you can see in set Y, it has its own only one element from set X. So 2 to 1, 4 to 0 0.5, 6 to 1.5, 8 to 2.5. Oh, wait. I'm sorry. Wait. Sorry. I confused you. Sorry. 6 to, what it was? 6 to 2, 8 to 2.5, and 10 to 1.5. So each of them has their own unique, what it was one? Unique outputs. And for the output, it has its own unique input. So this is what you call as the one-to-one. All right. This is one-to-one diagram. All right. Therefore, if the diagram is one-to-one, hence this is a, hold on. If it's one-to-one, this is a function, right? This is a function already because the diagram is one-to-one. All right. Next, how about this one? Let's just say I have um, the same numbers. All right. Same thing as the previous example. 2, 4, 6, 8, 10. And then here in set y, all right, let's just do 0 0.5, 1, 1.5, 2, 2.5. All right. Or maybe I could add one more. All right, I could add one more. So 2.5, let's just say 3. There we go. So let's again match. So let's just say I'll match 2 to 1, 4 to 0.5, 6 to 2, and then we have 10 to 1.5. And then for the 8, it matches into two elements from set Y, 2.5 and 3. So what type of diagram is this? So as you can see, guys, if you would notice here from set X, all right, so most of the element here has its own only one element of Y or element from set Y. However, one of them, which is 8, all right, 8, has two elements in Y or two elements in set Y, which is 2.5 and 3. So this is what you call as one-to-many diagram. So since this is one-to-many diagram, is this a function or not function? It's just a relation. So since it since in this diagram it does not succeed one of the condition here, because if you want to know if that diagram is a function, then make sure if it is either one to one or many to one. However, in this case, this is not one to one. I'm sorry, this is not one to one, nor it is many to one. It is one to many diagram. So this is just a relation, not a function. All right, this is just a relation. All right. Why is it called relation? Because it is what? A one to many diagram. All right. Unlike here, it is one to one diagram, which succeeds the condition wherein this one is already a function. All right. So again, how would you know if it is a function? Okay. The mapping diagram is a function if it is a one-to-one diagram or many-to-one diagram. Either of the two. All right. Either of the two. All right. One-to-one or many-to-one. All right. In this case, this is one-to-many. This is not many-to-one. All right. So this is just a relation, not a function. All right. So next, how about this one? How would you know if this is a function or just a mere relation? Simple. All right. Remember this one. There shall be non-repeating inputs. All right. Again, there shall be non-repeating, non-repeating inputs. All right. Hold on. There you go. So when we say non-repeating inputs, what are we going to focus on? We're just going to focus on the left side only. Okay? Left side only is the one that we need to look at the most. Make sure it is non-repeating, meaning it doesn't occur more than once. It will only occur once only, not more than once. So let's take a look for this as an instance, all right? 2, 3, 4, 5, 3, 2, 1, 0, 5, 8, and 6 and 10. 6, 10. All right. So let's take a look at the input. So we have 2, 4, 3, 1, 5, and 6. Okay. So The numbers here, okay, 2, 4, 3, 1, 5, 6, are they all the same? Are they? They are not, right? They are not the same. Hence, this is a function, right? This is already a function, all right? Because the numbers from the left, they are not all the same, all right? So next, how about for this one? Okay, let's take a look again the inputs. We have 0, wait, 0, 3, 0, 2, 3, 4, 4, 5, 5, 7, 6, 9. So let's take a look the inputs. We have 0, 0, 3, 4, 5, and 6. Are they all the same? Are they all the same? The answer is no. But let me ask you this question. Is there more than one number that have the same value as the other number? The answer is yes. And what are those? These two. Okay? What's the rule here again? Non-repeating inputs. Again, non-repeating inputs. All right? Meaning the inputs should never be repeated or occurred more than once. So as you can see, 0 and 0 exist twice. Therefore, this is not a function. Rather, this is a relation. Okay, this is not a function. Rather, it's just a mere relation. Wait, hold on. Let me fix that up. All right, guys. Again, this is just a mere relation. All right, mere relation. And last but not the least, let's take a look at this one. So we have a given of collection of ordered pairs or relation here. So we have 1, 2, 3, 4, 5, 6. Now, are they all the same? 1, 2, 3, 4, 5, and 6. Are they all the same? No. Okay. And each of them are all unique, such as these examples. You see this example? They are just the same. All right. But wait a minute. Wait a minute. Look at the output. You know, we have 2, 2, 3, 5, 6, 7. You see this one? They are the same, right? Yes, they have different inputs, but different inputs, but the same output, which is 2. So, does it mean it is a relation? The answer is it's still a function. All right. Again, what's the goal here? The goal here is non-repeating inputs. So 1, 2, 3, 4, 5, 6. Finish. It's already a function. So it doesn't matter if it has, what do you call this one? If it has a, what do you call this one? Sorry. It doesn't matter if there are outputs that exist twice or more than one. It doesn't matter. All right. Just such as this one, right? You see this? 2 and 2, right? So it exists twice. But again, it is not in inputs, okay? They are output numbers, all right? So as you can see, it doesn't matter. Again, it doesn't matter if the outputs, either one of them or all of them, exist more than once. Or it could be twice, thrice, so on and so forth. All right. As long as we're focusing the inputs here, 1, 2, 3, 4, 5, 6. Since the numbers in the inputs are not all the same, okay? Even two numbers are not the same, like each of them, it is called a function, all right? So this is just a function. That's it. All right. So to sum it up, how would you know if you have a given set of ordered pairs? All right. And then it is a function. Take the left side is the very important one. Make sure it has non-repeating. All right. That's it. Okay. So what before I begin proceeding to the next, as you can see, this first example and the second example, you can still call it as a relation, but since we have a special kind of relation wherein the inputs are not repeated twice or more than once, then it is still what called as function. All right. In this case, you can still call it as a relation in the second example, but not as a function. Because as you can see, the inputs, you see the inputs here, one of them or two of them are the same. So this is obviously not a function, but just a mere relation. For the first and the last example, as you can see, they are still called as a relation, yes, but in a special way. Because for the first example and the last example, their inputs are all unique. They are different. Hence, they are called as functions instead of relations. All right? Okay. So we can proceed. Table, the same thing as the ordered pair. Okay. So remember this one, right? We have x, y. All right. So let's take a look at this one. All right. It's going to give you what do you call this one? Two tables. All right. Hold on. So let's just say I have the numbers here. Okay, wait. I think that will better explain. So let's just say I have the numbers here like 0.01, 0.1, 1, 10, 100. And then each outputs are, let's just say, um, I have like 1.01. Then let's just say I have 2.33. Then I have 3.99. Then I have 475. Then I have 5 point um all right. So now let's take a look at this one. Here, the overall goal here is the same thing. Okay. Uh non-repeating inputs. All right. So as you can see, we have 0.01, 0.1, 1, 10, and 100. What do you call this one? Just a mere relation or a function? This is a function already. All right, this is already a function. Okay, and why is it that again? Because the inputs such as 0.01, 0.1, 1, 10, and 100, these are all unique. They are not all the same, nor some of them, both of them, or maybe three of them are the same. No, all right, that's wrong. All right, if that's the case. But as you can see, all of them are unique. Therefore, it is a function. It is a function. So yeah, it is non-repeating. So this one is quite easy to determine actually. So how about this one? All right, let's just say I have one. Wait, sorry, I forgot to draw the borderline. Let's see here. For example, there you go. So just say I have yeah, one, 3, 5, 7, 9, 11, right? And then let's just say I have what they call this one, 0.5, 1 half, um, 1, 1.25, and then I have here as just say 2, then 3. All right, that's so do you still consider it as a function? The answer is yes, it is still a function. All right, it is still a function. All right. So even if that there are the same values in y or your outputs, you still need to take a look at this one. I make sure it is not repeating input. So the same thing as the ordered pairs, non-repeating input. All right. So I think that is all that I could discuss. So thank you for listening. So this is just the introduction of function, and I hope you learned something. Thank you.